Thank you very much, Pepe. So yes, I'm Isabella. I realize I'm the only one talking about hydrogen density mapping these days, so I will give a brief overview to begin with. And then the core of the talk is that intensity mapping is hard, and so we are spending a lot of time in developing new methods in order to analyze the data. And we are also taking data meanwhile. We are doing the two things together. It's very informative for us, so we'll talk about method and data mostly. So why the 21 centimeter radiation is emitted by the hydrogen atom when it's in its atomic state, so just one atom. There's a positive and electron. When you have a spin click for the particles, you have the photon emitted. It's very good for astrophysics because the radio sky is easy to look at from far. There is no atmosphere absorption, and it's better isolated, so it's hard to be confused with other lines. So this is why it's very good for us. Although it's strongly forbidden, quantum mechanical forbidden, and this will come in a minute why this is a problem. So indeed, in astrophysics, we do use the 21 centimeter line widely. Most of the rotational curves that people have been discussing yesterday are made looking at hydrogen in galaxies. Here I'm showing just the most famous catalogs that are out there. But actually, we never heard about doing cosmology with these catalogs, right? And the reason is because this signal is very weak. Like with a state-of-the-art radio telescope, the very large array, you need something like 200 hours just to resolve one source, one galaxy. At least redshift here. So basically, it's unfeasible to collect all the objects that you need to collect in order to do cosmological studies. This will change a little bit with the SKA. I'll come to a second to SKA. But still, it won't be doing clustering in the usual way with the 21 centimeter line won't be game-changing. But the way they need to do things in the usual way, like pointing out the sources as we are used to, if we care just about the large-scale structure of the density field. And here comes the intensity mapping strategy. So the idea of, let's forget about actually resolving the sources. We will just collect all the radiation coming from the 21 centimeter at the different frequencies according to the different redshift we want to look at. And we read these maps. And we use these maps to do cosmology and large-scale structure studies. We can have as many maps as our channelization of the radio telescope can afford. So it's an unbelievable good redshift resolution, and we don't have any thresholding problems. All our maps are complete. So this will be. I mean, it's basically the wish list for a large-scale structure scientist, right? We can make very large areas because we scan the sky really fast. The redshift will be really good, so no compromise between photometric and spectroscopic. We have everything at the same time, and hydrogen is there until the epoch of ionization. So in principle, we can push this until redshift 6. Eventually, we want to do this with the SCA observatory. So it will be the largest radio telescope on Earth in basically the end of this decade. Probably you ever heard of it. It will be composed by two parts. One is South Africa, the other in Australia. These are some numbers. It will be a huge petaflops of data every hour. Here I'm highlighting the redshift that concerning the 21 centimeter line that we will be looking at. Either using the SK mid in South Africa or low in Australia. So eventually we want to do this. And indeed, among the proposed cosmology surveys proposed by the Cosmology Science Working Group within SCA, that intensity mapping the surveys are the priority, right? Here I'm highlighting what has been proposed by the community. And you can find in this red book all these numbers together with the science cases that we can look at. Of course, in combination with other cosmological probes, we can do planetary experiments. We can do BO. Very large areas means also FNL, so primordial non-Gaussianity. We can look after that. I wanted to include also this plot. Yesterday there was a discussion about dark matter, nature of dark matter, and how to distinguish the initial models. It will be really good the intensity mapping to distinguish among different dark matter models because there is no thresholding, right? We collect all the hydrogen out there, also the very small halos. So it means that whenever I have a universe with a little bit of discrepancies at the small scale end of the power spectrum, actually the whole signal changes through the whole scale that I'm looking at. you can ask me later about it. I mean, it's counterintuitive, but it's basically the intensity mapping observable highlights very little differences that you have in your power spectrum, for instance, driven by different mode of dark matter. I really like this picture by Bernard et al. Of course, having all this tomography of all these different redshifts allows you to do also this redshift dependent studies, like the H of Z. So records without the mapping information, then you squeeze the possibilities of this parameter when you add all this tomography in the game. So this is good. This is the future. What we will do, what we've done so far. I believe that just in one slide, I can reassume most of the detection that we have out there. This game began in 2010, so not so long ago, with this Green Bank telescope in US. There were some recent reanalysis of this data. Then I will talk more about what we're doing with MidCap in South Africa. Then we have the parks in Australia, but this is it, right? There is just another 2 instruments that are going after. It's few of us doing this. And one thing that maybe you've already noticed that all these detections are in cross-correlation either with galaxies or with quasars here, like sucking. Like there is no detection its own of the intensity mapping because it's really hard. Why it's hard? Because we have a lot of contaminants and it's very hard to disentangle them from the signal. We have a lot of contaminants and they are, I mean, very much more intense compared to the signal we're looking after. So this is the signal intensity, absorption of frequency. So basically I have all these maps. I'm piercing these maps around 1 pixel and my signal is noisy, right? Sometimes I have a H4 cloud, sometimes I don't. So the signal is this solid null line, is noisy. And then we have these huge foregrounds, sometimes 5 orders of magnitude higher, depending on where you look in the sky, but 10 to the 5 or getting intensity, especially that in theta between, but you also have the point sources and so on. So even if I know that that exceeds only the 1%, which would be really good, it would be still a disaster for us. So we are working in this regime. But one could think that, say, these guys here we have discussed already with the CMV talks before there's no swing property compared to the signal. So if I plot the information here on this parallel A perpendicular plot, okay, here near my information coming from the intensity mapping, and then the very short T parallel I'm lost because of these foregrounds. I can filter them out and then I'm done. But it is not the end of it, because then we have also systematics that interact with the foregrounds. The foregrounds are huge, so even very small leakages, like this is polarization leakage at type here is over 1%. So very optimistic for our telescope. The leakage is comparable to the signal. So we cannot really draw this line there and just filter out the foregrounds, or we cannot do parametric fitting. We cannot do sky models, at least not yet. So we go out and do some blind source separation and a signal processing sense. So we think about, this is the first thing you can do. You can think about your signal as a matrix, a cube, as frequency dimension in pixel. And the idea that you can decompose it in a mixing matrix minus some sources and components. So basically, you have n components in pixel space, that are modulated with this with the columns you are mixing matrix in frequency. And then the H1 signal is, as I said, almost Gaussian. So basically, once we do this decomposition, we are left with the noise that we can keep down by integrating, and the signal itself. But this is an imposed inverse problem, right? How do I solve for this? So I need something extra. The most common way of going forward when you have this kind of problem is, at least these two is the first things that apply, is either to exploit the correlation. So basically, you do a PCA. You generalize the covariance matrix and you solve for this, or you assume that your components are statistically independent. So then maximizing the statistical independence, you find the components, and this is called ICA. People have done this, and the important thing here is it's blind, but still you need to set this number of components you want to decompose into, and you need to pick that. And the higher this n, the higher is the chance that you are missing some signal because it's spilling on the other side of this sample. So n has to be low. What has happened in the past with these experiments here? They either use SVD, PCA, FastSCA, like a combination of the methods that I was discussing before, And these are the number of components that they've used, from 10 to 36 in just last year. Typically, in the theoretical works, 4 are enough. So I'm showing these numbers just to show you that like the big discrepancy between what we know so far about our data and what is actually out there. So we're trying to get to close this gap by either knowing better our instruments, but also working on the other side, both with the methods of the composition of the signal and also simulating the systematics that we need to deal with. So it's hard, but we are getting there. So as I was saying, let me first discuss the method that we are developing within MIRClass. So I don't with sparsity. Somebody has already mentioned it. It's another way to try to solve for this. There is a method in particular called GMCA that has been used already, that works with sparsity, has been used already in astrophysics, in the CMB, OR, and especially X-ray context. So what's sparse and why it's useful? Why it is useful for decomposing the data. So imagine that you have your signal looks like a sine wave. Then if you want to make it sparse, you need to find the domain in which it is sparse. So you go to Fourier space, right? So you are left with just one meaningful point number to describe your data. And once you manage to describe your data in this way, that means that the different components will be more sparse than the mixture of them, than the sum of them. And so doing this process, starting from the mixture and going back, it's easier. It's easier to disentangle them. So the algorithm can works in this way, in an iterative way. But here we're dealing with something like the galactic synchrotron. It's not, this is the histogram in pixel domain. It's not sparse. Doesn't sound like a good idea to do a Fourier transform of it. But if we were to transform it, things start to look sparser. So the idea of GMCA is to first decompose your data in wavelets and then to start doing exploiting the sparsity in order to decompose your data. And 3 years ago, more or less, this thing started, and already back then, we did a couple of things for the first time in the community, like pushing this idea that maybe this kind of approach is good for us. But then we even went further, and now we're working on something that we called mixed GMCA. So this is from a simulation. This is the angular power spectrum of one of our maps at this specific frequency. Doesn't matter. So this is what we want to get to, the cosmological signal plus noise, this solid light. And this is the GMCA using jog with the crosses. So it's working correctly. Here we are also plotting the signal that has been missed, that we lost forever, and the residual foregrounds in what we think is actual signal. So you see that the foreground leakage is less important than the signal that is missing. So we are fine. It's better to stick to these 3 components removed and not go further with scratching the data. But this is with the standard galactic foregrounds, synchrotron, free point sources. If we start adding some systematics, like this polarization leakage, things go astray, right? Look at here, there is a lot of leakage, and this is already with the 6 components removed. So, okay, let's remove even more components, and we go to 18 components removed. Things look better. Here we recover a little bit of information at the last scale. But you see that at the small scales, things were really fine back here, right? Here we are losing a lot of signal. You see that the level of the lost cosmological signal is entering this plot. So it's in the regime of what we are saving. So could have we stopped before, at least for the small scales? So different scales need different care. We realize this with simulations, but we also, this overfitting of the small scales, you can also see it with data. And so with this idea of using the wavelet domain, which is already a division in scales, spatial scales, and use GMCA on the small scales where we have a lot of artifacts, and PCA on the very large scales where we have these very smooth foregrounds. And we do this together and we call it mixed GMCA. We are already applying it directly on data. So I will show you some plots. So we're working with HeatCap. HeatCap is an array of 64 dishes in the range of Africa. It's a precursor of SK mid. So basically these 64 dishes will be one part of the 200 dishes of SK. So basically whatever we manage to do with HeatCap, it's good because we get a handle of what we can do with SK. And we are this correlation for the MIRClass. So we're running this pilot solver in intensity mapping. We are not that many people. So I can acknowledge all of them in just one slide. So please, these are the people that are also, I need to acknowledge for the work that I will show you. We started collecting the data in 2019. Now we have the third round of observation, but already with this data from back in 2019, we managed to calibrate it. There is this paper led by Ying Wang that shows it. So this is the final one of the final labs that we have in Canada. So basically, this is almost all sheet of them. We had another lab with Wiggle Z, which was good for a cross correlation. This is the scamming pattern that we use it, writing and something. This is like to show you that the analysis that I will show you later in this region where we were not so much RFI contaminated, so like a clean region in frequency. And in it, we managed already to measure a cross correlation with this Wiggle Z galaxy. So here I'm showing the final cross correlation that we managed to get with some null tests. So things are working, and I mean this is important for the road to doing this kind of thing also with the SKO. So this is super important for us that we managed to do this. So it's really our precious. So the idea was like, okay, let's use this as a benchmark to improve our pipeline. We can change many things in the way we are doing in analyzing our data. At least we need to redetect this, right, as a benchmark. And indeed, this is what we are getting now. So here is again the cross correlation between the same data cube, but with a different preprocessing and Wiggle Z. So this is what we got in this paper that I was showing you before as a benchmark in red. So you see the different lines are still at PCA with different modes removed. So we start with less than 4 and everything is compatible with 0. Then 4 and 5, I get the signal. So I'm removing enough to have a cross correlation between the intensity maps and the data. But then if I keep removing stuff and I go to 10 with this yellow, basically I remove too much signal and also the cross correlation is a negligible again. So there is this sweet spot which we can play with for the cross correlation. And please notice that now we're talking about 4 and 5 components, not 30. So this is very good news for us. It means that the leakage of true cosmological signal is less. So how much time do I have left? Okay, I will go really quickly on how we did this. First of all, PCA is very prone to outliers. So basically, whenever we went the PCA analysis before, we were down waiting with the noise that we have in the data. This is the heat map. So basically, the noise, this region of the sky, we look at it better because of our scanning strategy, we just had more data in the middle. So this way, we were down weighted. Still, PCA, the first 2 components that was removing was really looking after this systematics, whatever happening at the edges, and this was not good. So we started to be more conservative in terms of pixels, so to reduce the area in which we were looking at, but we could relax. Okay, I can skip this since we are a little bit late. But we relax a little bit the flagging in frequencies, because actually PCA looks for information, for components that are through this mixing matrix that has to be continuous in frequencies. So it's really hard for PCA going after jumps when there is where I enter flat channel. And indeed, I'm showing here the first 3 columns of this PCA matrix. Okay, I have this peak here because the variance of our map changes a lot. Maybe I can discard them a posteriori before doing a power spectrum analysis if I don't trust the channels. But still, for PCA to work, it's best to keep all the channels that we have and let the method do the job. The very first mode, maybe you really notice that this is very smooth. It's so smooth, then we thought, oh, maybe this is the synchrotron. It looks like synchro, or at least not on the map like. And indeed, we found, looking at this first component of this new PCA analysis, we found spectral indices which are compatible with the one of the galactic synchrotron, which was a good news. We know at least the brightest thing out there at these frequencies is shining correctly in our maps. Realize that we still do not know enough about our beam to the proper smoothing. So before people in literature have been resmoothing these maps in order to remove some of the impacts of the maps, just basically with a Gaussian beam. And this was not good. We're demonstrating it with this paper led by Marco Spinelli. So here is basically all the side lobes that we have in our beam. They're really messy. Somebody before me already said something about the side lobes that you need to deal with. That besides adding noise when you do this deconvolution, we also find that looking at the one-dimensional power spectrum in the line of sight, it was given even very weird effects that we kind of understood now, but not yet. This peak was really weird. So we just stopped doing it on the maps before we understand better how to do the deconvolution. And then we are going beyond PCA. We are trying different methods, fast ACA, Gaussian process regressions. Of course, here I'm showing my method, mixed GMCA. So basically, a really quick recap, we decompose the maps in large scales and small scales, and basically we run independently the decomposition on these scales before reassembling them in pixel space. So I can even choose a different number of components for the large and the small scales. It's the two things are independent now. So visually, how does it look like? If this is like a 4-component decomposition with PCA, with this data, you see here the galaxies are some point sources. Here the galaxies are already some defects, and here systematics. This is what happens with mixed GMCA. I have this PCA update on the large scales, so very smooth, and then GMCA deals with the small scale defect. And let me conclude with this plot. This is work in progress, but I can already show you that, for instance, the variance of the maps that needs to go down with the cleaning, the more the components that I remove, the less the variance of the maps, because I remove the foreground, so I should try to get to the noise as soon as possible. But here is PCA in gray, and this is mixed GMCA in magenta. So it's but of course I have mixed GMCA with the same number of components you move both at the large and small scale. But I mean, I could play around with this more, and we are doing so. So this is work in progress, but it looks really great. And I will skip this. So my summary. So I hope I convinced you that hydrogen intensity mapping will be a game changer in cosmology. We had our biggest problem at the moment are the contaminants, and we are working on it. MIRPLUS is ongoing. We are collecting data, so we are learning at the same time, data-wise and method-wise, how to keep going. Good news, we are detecting again this perforation signal, but with even better, I would say, with less cosmological signal loss. And we are trying different methods. They agree with each other, which is good. We understand the differences. I skipped the last part, but besides cleaning the maps, also trying to come up with some nice summary statistics that could also deal with the residual foreground is a plus. And this is it. Thank you very much.